Good. So what's the last thing? Fourier series. So we're going to do one more Fourier series problem, or maybe one or two. I'll put them on the homework right now, and this will be good to segue into the transform. So we have to have the complex and the real version. You know, we have to have it in our repertoire. I'm just going to write down the complex one though, which contains the real. And then we're going to get a limit out of this. E to the I kx, k equals minus infinity plus infinity. And the coefficients are given here by 1 over 2 pi. So we've got the 2 pi periodic function, that's minus pi by f of x e to the minus pi x dx. So we want to do one more example. I'll call this a homework problem. This one will lead to all kinds of good stuff. What we're looking for this time is the Fourier series, Fourier coefficients of a spike. So what we're going to do is define this function so that the area under it is equal to 1. Okay, that'll take us into delta functions and things like that as well. But for the moment, we're going to go from minus a to a. So f of x is equal to 1 over 2a for minus a less than x less than positive a, and it's equal to 0 for x greater than a. Or I could put the a less than x greater than a. All right, otherwise, because it's clear from the picture. Okay? And so the homework is simply to find, find the c sub k. And we'll find them both ways. So what about if we have the real series? This would be an even function. Okay, so we find the a sub k's. A sub k equals the real series. And you get a very interesting result here. In particular, you can check the result as a gets very small. As a gets very small, but since we kept this equal to 1 over 2a, the area under this thing is, of course, always equal to 1. So then we fill that in like so. So we'll have that as a homework problem, and we'll encounter this thing again when we do the limiting case now. So what we want to do next is the minus L to L Fourier series, right? We haven't bothered solving any problems explicitly with that because it's just, a sort of a harassment of things. This is a simpler version, but we do want to write these up because the next thing we're going to do is do the Fourier series from minus L to L and take the limit L goes to infinity. So that's our plan. L goes to infinity. And this problem here, you'll actually encounter it again. So yeah, that's on this Friday's list as well. Okay. So the next thing I do is write these expressions down, or I'll re-erase and start over again. So the second version of this c sub k, we had then we had c sub k was 1 over 2L integral minus L to L f of x e to the minus I k pi over L x dx. That you can just gain by simple substitution. I think I illustrated it clearly enough. But what about the limit L goes to infinity? If L goes to infinity, I can't just plug it in here or here or here. So I have to do an interesting limit. So the limit as L goes to infinity, question mark. Now I have this interesting construction I'm going to put up, but it's kind of involved, so I'm going to first just write down what the result is going to be. Okay. So the result as L goes to infinity is the following. We end up writing our function 1 over root 2 pi, we'll see where that comes from, minus infinity to plus infinity. The coefficients are turned into something we're going to call f hat of k. They're still functions of k, just as the c sub k were dependent on k as well. E to the I k x dk. And what's nice about this formalism here is the symmetry of it. So f hat of k is defined as 1 over root 2 pi minus infinity to plus infinity f of x e to the minus I k x dx. So you'll notice over here we have a function of x, the argument x appears up there, and we're integrating over the k, right? And down here, function of k appears up here, and we're integrating over the x. This is called the Fourier transform. Fourier transform. Let me go ahead and get the board just through. Fourier transform. And you can see where it comes from. It comes from the Fourier coefficient. And what we're going to do is a few interesting calculations with this today. But for the moment, since I have it in my notes, I went through all this trouble. I'm going to show you guys this actual limit formally, because you see it's a little tricky. Like I said, you can't just plug these things in and get this. And this is something I did. I wasn't satisfied with the crude version of this that I had seen in a book. So this will be something you guys can take down for your notes. So anyway, this is going to be a couple steps, but before we move on, you can see how nice and symmetric this thing is. So this is a really useful form, and it's restricted to functions that vanish at plus and minus infinity. Okay, they have to vanish fast enough to be safe. Okay, so let's see how this thing was constructed. The idea is to plug this expression into this one here. Okay, so that's the first thing we're going to do, and we're going to have to use a different subscript, which is fine. So I'm going to plug the one expression into the other, And I'll write down every step, but take C sub k into f. We're going to get the following: f of x equals, I'm going to use summation index n, 1 over 2L, integral minus L, positive L, f of u, e to the minus I n pi over L, u du, e to the I n pi over L x. Okay. So making sure we see where that came from. I just plug this in, I'm using Hanford subscript. So now, I'm going to do one more intermediate step, okay? So I'm going to pull out this 1 over 2 pi, and I've got this summation here. Since I have a pi here, I can have a pi over L, and the same thing, okay? Minus infinity plus infinity. Same thing I had before. I n pi L u du I n pi x over L. Okay. Now the reason I've done this, we're still summing over n, is because as L gets larger and larger, you can see this summation here as being an integral. This is the small differential in the sum, okay? So you can see this as being an integral, and what we have to do is turn the thing, what I'm going to do is, this is going to become an integral. I'm going to turn this integral into a Riemann sum as well, okay? And I'm going to have a double sum for the double integral, and then I'll be able to do the limit carefully, and the double sum will turn into the two integrals as well, okay? So that's what we're headed for, and here's my construction. F sub n of x, I'm going to go ahead and pull the 1 over 2 pi out front. The trick here, took me a while to figure this out, is to go from minus n squared to plus n squared. Kind of squeezing it about that. I've got a 1 over n for that differential. I have another sum, j equals minus n squared plus n squared. F of j pi over n e to the minus I n 1 over n j pi over n e to the I n over n x pi over n. Okay, I'm going to box this in. Talk about it. Okay, so what I've done here, so to get from here down to here, we're letting L equal n times pi. So as n gets large, you know, L goes to infinity as n goes to infinity. We're going to let k So what's going on here with this n squared business is that when j is equal to n, okay, if you look at this thing right here, when j is equal to n, here I'll point. When j is equal to capital N, I just have f of pi, right? But I'm gonna run not from n, but to n squared. So when j is equal to 2n, I'm at 2 pi. When j is equal to n squared, I'm at n squared over n is n, I'm at n pi. Okay, so that's how I'm going across this thing symmetrically. And the larger n is, the smaller that differential is. So this really turns into the double integral I'm about to write down. Yeah. And the 2 pi, I can add, well, I erased it. That 2 pi is going to be distributed as 1 over root 2 pi to either half of the whole argument. So yeah, this construction, you know, you can study on a rainy day. I'm going to write down what we get as we take this limit now. So as n goes to infinity, we're going to get the entire axis on both of these right here. So we'll make those substitutions. So we're getting, as n goes to infinity, we are getting f of x equals 1 over root 2 pi integral dk 1 over root 2 pi f of u e to the minus I k u du e to the I k x. So minus infinity to plus infinity. So I've distributed the 1 over 2 pi to each of these integrals. Here we go. So you can admire all these now. Right, so there was your dk right there. This thing I distributed 1 over root 2 pi. That was the f of u e to the minus I k u du. Yeah, that du was in there. So these have places switched. But there you have it, and that is your Fourier transform, and that's your function. So that's why you have 1 over root 2 pi integral dk, and then here you have the f hat of k, because we're integrating over the u, so k is the argument e to the I kx. So there's the construction. Study that if you're interested in Riemann sums. We're actually going to be talking about Riemann sums here and there, so this is kind of a extreme one. Yeah, when I first did this, I was going end to end, and I was saying, wait a minute, you're not getting very far. But so the whole trick is that n squared, and that takes you out both directions on the axis. Good. So let's do some applications of this now. And the first application is going to be the version that was the homework problem a minute ago, okay, except with the Fourier transform. Okay, so we'll set up the Fourier transform formulas over here and just use them repeatedly. So we now are looking at this problem, 1 over root 2 pi minus infinity to plus infinity, f out of k e to the I kx, k and Fourier transform 1 over root 2 pi Good. Okay, so like I said, the first example is that same spike we had as a homework problem with the series. So we're looking at this same function, minus a to a, 1 over 2a, x-axis, and 0 everywhere else. Okay. Equals 1 over 2a, 0 otherwise. So what about the Fourier transform of this? The idea should be pretty clear. We're trying to do the same thing we did with series, except with a continuous function, right? With both of these being continuous. So, f at k, we're just going to root 2 pi. And the boundaries of integration are now minus a to a, 0 otherwise, and the function is 1 divided by 2a e to the minus I kx dx. So we have 1 over root 5, 1 over 2a, 1 over negative ik e to the negative I kx, and then I move from minus a to a. So root 2 pi over 2a, over negative ik. And yeah, we have here just e to the negative I k a minus e to the I k a. So here's where we want to recognize a couple of things. This, or the trait functions that are buried in here. So I can actually take the e to the I k a minus e to the negative I k a divided by 2i. So if I factor that out, got rid of that minus sign, took the 2 over there, so it's 1 over root 2 pi um, 1 over k times a. Okay, we were talking about this one yesterday, right? So everybody recognize what I have right here? What is that? Anything in parentheses?
It's the imaginary part, right?
Divided by, yeah.
Well, no, just the imaginary part.
Of Euler's formula.
Yeah.
So that would be sine of Ka. So that's the sine of Ka. That's the kind of thing we want to start to recognize. Here, I'll use this little piece of board. So what we got for this f hat of K is equal to 1 over root 2 pi sine of Ka divided by K times A. This is something you run into in optics. If you haven't yet, you will. So what we're going to do is juxtapose graph this, we would have to have a k-axis, right, not an x-axis. But otherwise, it would be well behaved. Yeah. So I'll erase this calculation. What does the graph of f hat of k look like? We've got our f hat of k, the k-axis. Got 1 over root 2 pi. As k goes to 0, we've got that indeterminate form, but we know this one pretty well, right? Sine of ka, leading term is ka divided by ka. So this just goes to 1. We've got that 1 over root 2 pi. And when does it have its first 0? There's going to be a sort of an envelope, 1 over ka, but it's when ka is equal to pi over 2. Pi, sorry. When k is equal to pi, so if you go out to pi and negative pi, you get your first 0. Then where's the next 0? 2 pi. Okay. But it's decreasing considerably as the 1 over ka. So,
Should there be a negative sign in there?
sorry.
Should there be a negative sign somewhere in there from the negative IA?
I took care of that when I wrote the sign down. The negative was absorbed because it was ka minus negative ka, not ka. It's there. Anybody have it? I just erased it. The negative sign was absorbed when I wrote that because I had this e to the negative ika minus e to the ika, and I flipped those around to get the imaginary part. So yeah, we got that. Okay, so where were we? Here we go. We've got this thing and it gets smaller and smaller. Of course, that's not pi, that's ka equals pi. So ka equals pi, k equals pi over a, which is also important. 2 pi over a, k 2 pi over a. So this graph has a very interesting property because the original function, this spike here, as a gets narrower, or as a gets smaller, this spike gets narrower and higher. Whereas the Fourier transform, as a gets smaller, this maximum here gets wider. So that inverse relation between the Fourier transform and the original function is crucial. When you guys study the Heisenberg relations, formally you're going to actually use this very property to get, you're going to have delta p and delta x. And it's actually going to be delta k and delta x. So here you would have a delta k, if you have an uncertainty, you'd have a delta k, I'm sorry, a delta x that's this y, and you'd have the corresponding delta k, it's that y. So that's the important note here. Note width of f of x spike is, I'm just going to call it delta x equals 2a. The width of f hat of k is delta k equals 2 pi over a. Okay, so you've got that inverse relation that we're going to see again and again. Saw it here first, and this is a perfect example for that. So the other example we want to do is the Gaussian. So this is nice, but here we start with a function that's not differentiable, and we end up with something that's nice and smooth. we want to have both of our functions being smooth. So that's going to be the next one here. Maybe I can assign the Fourier transform while we're at it. I think I will. This one won't be differentiable, but it'll have the advantage of being very nicely interpoled. So here's an interesting problem. Suppose we have f of x equals, I'm gonna say, a e to the minus alpha x magnitude. So first we look at this thing, and it's equal to a right here, and I've just constructed it to decay exponentially left and right. So we would want to get the Fourier transform of this function. So find f at of k. In fact, no, I have a better idea. Only a such that integral f of x dx minus infinity plus infinity is equal to 1. So we're doing on this integral what we just had trivially on that spike. Okay? So we just have to do this integral here and then find the value of a that makes the integral equal to 1. So we can either normalize it that way, or we can even square it. We'll normalize it this way. We have time to do the other way as well. So that's the first thing. And you can see you're going to break this up into two integrals, one from minus infinity to 0, one from 0 to infinity, so you won't have to deal explicitly with one of those ways. Break it up into two integrals, get the value of constant a. The second part of the problem is going to be to calculate f at k. And what you're going to see is the same feature. So this one gets narrower for alpha getting larger. And your f hat of k is going to get narrower for alpha getting smaller. Okay? You'll find that relation here as well. So calculate f hat of k. And that'll be a good homework example. And I'll get started with the Gaussian. Let's see what formula we use for the Gaussian here. Okay, so we got this. I think I'm going to do some of this. Okay, good. We have to do an e to the minus ax squared. Okay, so in our next example, we're taking f of x is equal to, I didn't normalize this one. Yes. A e to the minus a x squared. So we want to do the same thing we have on this project here, it's a little more involved, okay? A e to the minus ax squared, and we're going to normalize it so that what we have, this time we have a totally smooth function. Okay, so this is the one that really works for a lot of things. This one, this one's not differentiable at the origin, so it's not quite as useful as the Gaussian is the real deal. So what we want to do first is find A so that this thing is normalized. So same as before, find A. So that we're squaring it. Yeah. So that integral f of x dx minus infinity plus infinity is equal to 1. So this is an interesting problem in its own right. What we're going to do is we need integral a e to the minus ax squared dx is equal to 1, so we can also say we square this thing and it's equal to 1. If that's the case, we can have a squared integral e to the minus ax squared dx times integral e to the minus ay squared dy is equal to 1. And we'll go ahead and open this up. So we're going to normalize this, and there's a famous trick here. So we've got this a squared. We have e to the minus a x squared plus y squared dx dy minus infinity to plus infinity is equal to 1. Okay. So far so good. We can put it under a double integral. We're in the entire real squared plane. Ax squared plus y squared. We can do a transformation. We can have e to the minus a r squared using plane polar coordinates, and the dx dy is going to be r dr d phi, and the d phi will go from 0 to 2 pi, and the dr will go from 0 to infinity. So this allows us to have a squared. The d phi integral is trivial, so we just have 2 pi. And the other integral here, we can let u equal r squared du is equal to 2r dr. So we end up with the e to the minus au, and the r dr is du divided by 2, which I'll do right there, 0 to infinity equals a squared pi 1 over minus a e to the minus au, 0 to infinity pi, so pi a squared over a. E to the minus infinity is 0, e to the 0 is 1, that gets rid of the minus sign, equals 1. That means a equals square root a over 5. So that's a useful one. And so now we have a function that's always equal to one. So now we can say f of x equals pi, I'm sorry, a over pi root of e to the minus ax squared. So that's the function whose Fourier transform we want to find. Good, and your normalization problem will be similar. Yeah?
Why is it valid to split up the dx squared into a dx times dy?
Because we're integrating two, because this is an integral along the real axis, right? This one here, this original one, x, and if we treat this one here as an integral along the y-axis like that, so then we can multiply together. That's what we're doing, because we're doing the entire plane. Right? If we had certain bounds, it could be more difficult. We're doing the entire plane, entire R squared plane. Good, so there we go. We've got this, and this next one, I may lead you guys to do part of it. Let's see though. So we have f of x now. We have the normalization. F hat of k is equal to 1 over root 2 pi integral minus infinity plus infinity. F of x, I'll just use the letter a for the moment. A e to the minus a x squared e to the minus I k x dx. So yeah, this is the one we want to get here. And I may skip some steps. Let's see here. 45. Minus infinity plus infinity. I'll bring a out front. So what do we have here? E to the minus a x squared plus I k x dx. And what we're going to do is complete the square here. Complete the square. I have that here. I'm just going to write this out. So we've got that a over root 2 pi minus infinity plus infinity e to the minus a x plus I k over 2a squared e to the minus k squared over 4a dx. And in fact, what we can do here is just test this. We've got minus a x squared minus I k over a x minus k squared over 4a. And this minus times minus is plus, and so that gets rid of that one there. So that's the correct expression there. And in fact, I'll just write this out here as well, minus k squared over 4a. There's good. yeah, this is just formal. And here's where it gets interesting. So we go ahead and erase this. So we'll go ahead and have the a over root 2 pi. And this, we're no longer integrating over. I can pull this out, e to the minus k squared over 4a. So now I'm looking at this integral here, plus infinity, minus infinity to plus infinity, e to the minus a x plus I k over 2a squared dx. Now, this is a complex argument here. Okay. Now, formally, I can let u equal x plus ik over 2a. This is just a constant, and my du is going to be equal to dx. So I'm going to do that. A over root 2 pi. Oops, put this thing under first. E to the minus k squared over 4a. And you can almost say we're done, right? E to the minus au squared du, because we just did that integral. We just did that integral. But what about the boundaries of integration? What does it mean to say minus infinity to plus infinity? Because here I would have minus infinity plus ik, right? Plus infinity plus ik. So the boundaries of integration are interesting here. By the way, this calculation works. We can just blithely go ahead and do it. But we'll make up that thing here. So I'm just going to put, minus infinity plus ik over 2a plus infinity plus ik over 2a. I'll put little question marks here. What's going on with the boundaries of integration? If we pretend there, or if we say there's no problem, we can just go right through there. Okay. So I have an a over pi, and I'm going to have a pi over a, and we'll be good. Let's go ahead and do that. So 1 over root 2 pi e to the minus k squared over 4a, and then the a was root a over pi. From the integral, it's going to be root pi over a. Those are going to cancel. And I'm just going to have this here left. Okay. So let's go ahead and put this in here. I get f hat of k 1 over root 2 pi e to the minus k squared over 4a. So what we're going to do is focus on both of these now and really see what's going on. And as far as this integration goes, it is completely justified. We're going to study complex analysis enough to make all those proofs totally rigorous. For the moment, it's kind of a conundrum. And in fact, I'll just show you a small picture. If you were integrating from minus, infinity, just say some capital R, but instead of, take limit R goes to infinity. Instead of these 2 points, R goes to infinity, you're sending those out. What's formally being done, or what's actually being done, is we're integrating along a path like this. So we're integrating from this endpoint to that endpoint. And that's suppressed right here. The reason it's legitimate is that when you're taking these out to infinity, the contributions here just completely vanish. Okay? Contributions as you go out to infinity. So when we study complex analysis, we'll be integrating all over the complex plane. Right now, this is what we're implicitly doing for this integral to work out. Okay. So yeah, let's just take a look at both of these now that we found them, and we'll study their graphs. So this first one here, we had f of x was root a over pi e to the minus ax squared, and then it's Fourier transform 1 over root 2 pi e to the minus a squared over 4a. So let's graph both of these together now. Good. Again, so what do we have with this graph here? That's just the Gaussian. And this too is just the Gaussian. Now with some normalization here. So we can actually draw both of these. But you can see as A gets large, I'll do it for large A. As A gets large, this thing gets taller and narrower. Okay. As A gets large. Because it gets taller because we've got the square root of A here, and it gets narrower because that is suppressed so rapidly. As A gets large here, this becomes, this factor in front gets smaller. At k equals 0, it actually retains the same height. There's no scaling factor here. So as A gets larger, we're just looking at something that goes like this. So what about the limit of A getting very large? A gets very large, we have just a pure, very narrow spike. Here, we essentially just have that's a flat thing as far as you want. Okay, so we're gonna make use of these exponentials quite a bit. And this is a totally standard result. Let's see what we can do with this. I'm going to add one more homework to this mix. And that's going to be to reverse this calculation and get this one back again. Okay. So take f hat of k into f of x equals 1 over root 2 pi. So you take this into here, and you're integrating over k, and you basically do the exact same steps I did, completing the square. So you know it's going to come out here, right? You're going to take this thing from here, right, into this expression, do the integral, same argument with the boundaries, so everything will be safe, and then you should obtain what we started with, right? F of x equals root a over pi minus ax squared. That's a good condenser. If you reverse that calculation. So let's see where we're going to head with this. There's a number of great applications. We'll do a few applications before we start doing the complex analysis in the complex plane. get a little practice on this. Here's where we're headed. So next, some more functional relationships. Functional relations with the Fourier transform. There's an applications with differential equations, but really we have to do complex analysis. So let me briefly explain what that is, and then we'll come back to this. So this is what we actually have to go through to really work the applications on Fourier transforms. And what we have to do is learn to do calculus in the complex plane. So very generally, we have to be able to just do integrals from A to B that, do any number of things. Okay? And what we're going to find is that the functions in the complex plane that are differentiable, okay, have a lot of really great properties. Okay? They're very, very well behaved, and we learn to do all kinds of interesting things with the complex functions. We've gotten a little taste of it because we had e to the I, theta, or e to the ix, right? So we're getting used to Euler's formula, but we're going to generalize this to just, and when we did e to the I theta or e to the ix, we were on, say, we'll just talk about this one, we were on the x-axis, right? We were doing an integral on the x-axis. But we saw with this example we just did, we actually have to leave just doing an integral on the real axis. So what we're going to do is e to the z, right? And z is just anywhere in the complex plane, and we'll get some very nice properties. And then we'll come back and do these applications and things. That's the best way to do it, because the Fourier transform, so this thing here, these two integrals, in order to really evaluate them consistently, you have to be able to cruise all over the complex plane. You can't just be restricted to the x-axis the way we have been for our couple of examples, because we already saw we branched out of that on this calculation. Okay? So that's where we're headed, and this is a really great subject. I mean, you could go to the math department and do a full semester of that subject and not regret it either. Okay? But we'll get a good taste of it. So that's where we're headed. That's all I've got for you today. So we'll talk about this a little more, but then we'll jump into complex analysis, complex functions. Good.